All right, today we're going to be looking at velocity versus time motion graphing. The objectives for this video are to be able to identify speed, velocity, acceleration, and distance and displacement traveled from a velocity versus time graphical model. We examined the equation v equals d divided by t in the last video when we looked at distance versus time graphs. This bar above the v indicates that it's the average velocity. The units are meters per second. Now we need to speak about acceleration in order to look at the next type of graph. So acceleration indicates that something is getting faster with time. So here the car is going from 0 meters per second to 3 meters per second in 1 second. Then it goes from 3 meters per second to 6 meters per second in another second. And then from 6 to 9 in another second. The speed increases by 3 meters per second for every second. We can also say that as the speed increases by 3 meters per second, or 3 meters per second squared. There are two especially important parts of a graph in physics, and that's the slope and the area. We already examined the slope in a distance versus time graph. Now, if we manipulate this equation v equals d over t, we can find out what the distance is. So I can solve this for you a little bit. V equals d over t. And this just comes from the distance versus time graph. But now we want the distance. So we multiply t on both sides, and we get distance is equal to velocity times time. And that's the same as this equation here. So that equation is actually the same as the area under a velocity versus time graph. If you look, this is length times height. This is equal to area of a rectangle. And if the object is moving at a constant speed, we get a rectangle, and we'll see how this works. Oops. So in 1 second, right there, it will travel 10 meters when it goes 10 meters per second. Then after 2 seconds, it goes up to 20 meters. After 3 seconds, it has now traveled 30 meters. And then after 4 seconds, it has traveled 40 meters. On a different type of velocity versus time graph where the object is accelerating at a constant rate, in order to find the distance it has traveled, you have to find the area under this whole graph. Now, that might look a little intimidating, but if you remember back how to find the area of a strange shape, you just find the triangles and the rectangles. We already found the rectangle area, and we said that it was the same thing as 40 meters. But then we can add the triangle on top, and it's 1/2 of this same rectangle, just because it's going up another 20 meters per second at the end. But a triangle, the area of a triangle is only 1/2 that of a rectangle, so we actually are only going to add another 1/2. So that makes it so that the answer to this would be 40 meters plus another 20 meters, because 20 is 1/2 of 40, and that's 60 meters. And that's how far this object traveled over the whole time. So here is a graph that is a velocity versus time graph. You have to notice here that it is velocity that we're looking at and not distance. So this is looking at how a helicopter traveled, and it asks, what time did the helicopter have a negative acceleration? So the negative acceleration, you can see just when it has a a negative slope. So then it asks for, so this is 8 to 10 seconds. So we can write that here. And then it says, what was the helicopter's acceleration at 1 second? This is 1 second. It is accelerating at a constant rate, so that means that we can just take the slope and we say 100 meters per second. That's its final velocity. And its initial was at 0, so that makes it easy. 100 meters per second minus 0 meters per second is equal to 100 meters per second. And that happened over 2 seconds. So then if we take the slope, it's just a change in 2 seconds. So that's equal to 50 meters per second squared. Okay. Then what was the helicopter's acceleration at 3 seconds? Well, at 3 seconds, the helicopter is not changing its velocity. So if it doesn't change its velocity, it is not accelerating. So this is 0 meters per second. That's pretty simple. What was the helicopter's average acceleration for the first 4 seconds? So 4 seconds is here, and we want the average acceleration. So we can actually get that just by using the slope of this line. It's the average. So then we can say 100 minus 0, and that's in meters per second. And that is divided by 4. So it's equal to 25 meters per second. That is meters per second squared. That is its average acceleration. And then I'm just going to clear this up. It says find the average acceleration between 6 and 10 seconds. So to do that, again, you're just going to take the slope, and it's going to be final, this is 0, minus the initial, which is, let's say, 140 meters per second. And that happened in 4 seconds. So this is a negative, and acceleration, it didn't ask for magnitude, so it does want the sign, so it's negative. And then, let's see, 12, 35, I think. Yeah, 35 meters per second squared. So this is a negative. And then it asks for the instantaneous velocity at 6 seconds. So when it wants the instantaneous velocity, it wants the velocity that is occurring right there at that time. This one's pretty simple just because it's not moving. So we can just kind of come and read it over. And it is 140 meters per second. And then it asks for the average velocity from 4 to 8 seconds. So this one is a little bit tricky, and everyone always forgets about this. It's not an equation on the reference table, but we start at 4 seconds. So it's 100 meters per second. And then we go to 8 seconds, and that's 200 meters per second. And it's just asking for the average velocity. So then we just have to divide by 2 because we have 2 velocities. So that's 300 meters per second divided by 2. And that's equal to 150 meters per second. That's the average velocity at that time. Okay. All right. There are some things that you have to make sure to remember. You have to make sure that you don't mix up the different velocities. There's the initial velocity. There's the average velocity here, the change in velocity here, and that's just the final velocity minus the initial velocity. And then the instantaneous velocity, that's the velocity that occurs at a specific instant in time, like at 5 seconds. Okay. So then just a review of what different distance versus time and their associated velocity versus time and acceleration versus time graphs look like. So a distance versus time graph that shows the same location from moment to moment, that's going to mean that it has a constant velocity of 0, and there isn't an acceleration either. Then we have another example where the distance versus time graph is changing at a constant rate, and that means that the velocity is constant, but it also means that the acceleration is 0 meters per second. It's down there at the bottom. The speed wasn't changing. Now here's one where the distance versus time shows that the distance is changing more and more from moment to moment, which means it's accelerating. And then the velocity versus time graph is going to go up at a constant rate because it is also accelerating. And then acceleration is some non-zero number. It could be negative, but in this case, the velocity versus time slope is positive, so it's likely to be positive. It will be positive. All right. Thank you. That's all I have for you today.